What is up, guys? We're going to be taking a look at this lab, exploiting DOM clobbering to enable cross-site scripting. Let's just start off by saying there is a reason why this lab is in the expert category. There are quite a number of moving parts and also counterintuitive aspects to this particular vulnerability. Don't worry too much, we're going to cover everything. The starting point here has to be what exactly is clobbering. And although it can refer to a few different things, the general idea behind clobbering is that there is a location in memory that's unintentionally, or intentionally in the case of a hacker, overwritten. A simple example could be, imagine some source code that's stored in a repo somewhere. If a developer were to push an outdated version of the code to the repo, overwriting the new code, that would be an example of clobbering. Now, in the case of the developer, that's obviously unintentional, whereas a hacker may do this purposefully in order to change the way that a certain piece of code executes. Imagine, for example, a web page makes use of a function, and that particular function relies on a variable at some point. Now, ideally, we'd love to change the function itself, but let's imagine we can't inject into that function at any point. If we could change or overwrite the value of the variable that that function depends on, that's a very similar outcome to being able to inject into the function itself. That's really what clobbering is, overwriting key variables that the page is depending on for its functionality. Now, to lay the groundwork for this particular attack, there are some prerequisites. Take a look at this fairly simple HTML document. We have a title, DOM Clobbering. This page consists of two anchor tags. Note that they both have the same ID. That's typically something we're not supposed to do in HTML. An ID should be unique to a single element. Notice that both of these anchor tags have href attributes. We have first link, we have second link. The second anchor tag there also has a name attribute, URL, and we can see that they have the text first element and second element. So here is the page in the DOM, and the first interesting thing to note here is that if we try and access window.link, we get a HTML collection returned. Now, a HTML collection is essentially an array, and it consists of HTML elements. We can also access the individual HTML elements by accessing certain indexes on the overall HTML collection, very similar to what we do with an array. So if I head to window.link index 0, we actually get the first HTML element returned from that HTML collection. And if I hover my cursor over that in the DevTools, we can actually see first element highlighted on the page itself. So naturally, if I head to window.link index 1, I'm now going to be able to access the second HTML element in that HTML collection. Once again, if I hover my cursor over that, I can see it highlighted on the page. This is non-standard browser functionality. By non-standard, we don't mean that Chrome is the only browser that supports this type of functionality, where a property is added to the window object based on the ID of an element on the page. When we say it's non-standard, we mean that this behavior is not part of any official web standard. There's not only one way of implementing this particular behavior. This means a couple of things for developers. The first is that different browsers may implement this differently. And the second thing is developers should not generally rely on this particular functionality of the browser because it could differ from browser to browser. Now, there's another interesting attribute to this particular behavior. Remember, we had a name property on that second link. Well, if I visit window.link, which we know is going to return the HTML collection, but I then look at the .url property on the window.link collection, it actually returns the HTML element that has that name attribute. So when I visit window.link.url, you can see that I actually get that second anchor tag returned. Here is the exact same page in Firefox. Let's visit window.link. Notice that we don't actually get a HTML collection returned now. We simply get the value of the first element. We visit window.link.url, we get undefined returned. So two different mainstream browsers, but different functionality in terms of how the window property is assigned depending on the value of the ID of various elements on the page. The lab guidelines say that this particular vulnerability only exists in Chrome, and it's to do with the functionality we've just seen. We can't access that second element through window.link.url. In this case, we just get undefined returned. So Firefox is not going to work for this particular vulnerability. Returning now to Chrome, let's consider the difference between a JavaScript object and a HTML element. If we make use of the JavaScript type of operator and pass window.link.url, we actually get the type object returned. This is because a HTML element is a type of JavaScript object. It's a JavaScript object that follows a very specific pattern in terms of the properties and methods on that object. We very often colloquially use the term DOM node to describe a HTML element. Does window.link.url match the pattern to be defined as a HTML element? We can make use of the JavaScript instance of operator to find out if the object matches as a HTML element. So window.link.url instance of HTML element. This is going to return true or false. We can see we get a true response here. So we've determined that window.link.url is of type HTML element. Now, if everything seems abstract at this stage, don't worry too much. You'll see why this is prerequisite knowledge for solving this lab. So based on what we've seen so far, let's fire up the lab. We see that it's a blog. Let's fire up the first post in the list. Has a post ID of 1. We can see a blog post and the ability to leave a comment on the blog. Now, taking a look at the lab walkthrough, it has the text, this page for a specific blog post imports the JavaScript file load comments with DOMPurify.js, which contains the following code. This is actually incorrect. This is not the name of the JavaScript file that contains the following code. The file of interest is load comments with DOM Clobbering.js. If your developer ever gives the JavaScript file the name load comments with DOM Clobbering, you have bigger problems than trying to solve a Portswigger lab. This is another example of a file that's named after the vulnerability itself. One of the things that we want to focus on before we have a look at the JavaScript is that for each of the comments, there is a small image, which is really a placeholder for an avatar in this case. There is a default avatar that loads up. That's why all 3 comments have the same avatar. I guess the idea that the developer had was to have some custom avatars at some point further down the line. Let's have a look at how the logic for these avatars is implemented. We won't look at all of the JavaScript here, but we will get a high-level overview of the JavaScript document. So we have a function here, load comments. So this is going to be an asynchronous request to grab the comments from the server and then load them onto the page. We can see that after data is returned from the asynchronous request, it's passed to the display comments method. Further down in the JavaScript file, we have the actual display comments method being defined. You can see comments is passed to that as a parameter. Mostly this particular method or function is DOM manipulation. We are setting up things like paragraphs. We're placing the text for the comment inside the paragraph. The area of interest for us in this JavaScript here, we see let default avatar being defined. We then have an OR operator. The value of default avatar is either going to be set to window.defaultAvatar, which presumably doesn't exist at this stage. There's nowhere in this JavaScript file where window.defaultAvatar property is actually defined. So it may be a placeholder for later code. But the point is, it's still functional part of this code right now. If window.defaultAvatar did exist, and we could assign a value to window.defaultAvatar, well, it would now become the value of default avatar, which then goes on to be used later on in the JavaScript. Now, assuming that window.defaultAvatar doesn't exist initially, then the value of avatar is going to be set to resources, images, avatar default.svg. In other words, the image file of the default avatar, which we just saw loaded up several times on the page. So here's the interesting question. Can we manipulate the value of window.defaultAvatar? Because looking a little bit further down the code, we see another variable being defined, avatar image HTML equals, and this is where the actual HTML for the avatar image is written. Image class equals avatar, then we see a dynamically assigned source attribute. So really your alarm bells should be absolutely going off at this stage, because not only do we have dynamically assigned source attribute, but we are concatenating to a HTML string. Anytime we're writing HTML as a string, we can potentially run into some pretty serious security issues. What is being concatenated as the value of that source attribute? And we see that the answer is a JavaScript ternary. So if comment.avatar exists, then concatenate escape HTML comment.avatar. But let's assume that it doesn't exist. What's effectively going to be added here is default avatar.avatar. So if we're able to manipulate the value of window.defaultAvatar, and we're also able to set a property on window.defaultAvatar of .avatar, then we're going to be able to inject into the value of this particular source attribute. So to see how this works, let's create a new comment on the blog. we're actually going to simplify the payload that solves the lab and work up to it. And the first thing we're going to do is have a very, very simple injection into the payload here. We're just going to type the string Zen shell. So what do we have here? We have two anchor tags. Remember our test document from earlier. Both of them have the same ID, and in Chrome that's going to mean they will be generated as part of a HTML collection on the window.default avatar property. We can see that the second anchor tag has the name avatar. That means it's going to be referenceable through window.default avatar.avatar. And we can see that the href of that second anchor tag is Zen shell. Now we know that HTML is going to be allowed as part of the comment here. How do we know that? Because there's a directive here above the comment box. HTML is allowed. Again, possibly something that might set off alarm bells when you see a message, HTML is allowed. Maybe it should be allowed, but only if there's the correct security mechanisms in place, which often there might not be. Now we do have to fill out some default information here. So we need to type name and email, and we need to type in a website. So feel free to fill in some arbitrary values for this. It's really just to pass the front end verification, because if we don't fill out these values, we won't be able to post the comment. So let's post the comment. Let's head back to the blog. Let's fire up the DevTools. Now let's have a look at window.default avatar. What do we expect here? We expect a HTML collection. Well, we have it. We have a HTML collection containing two HTML elements. So what was initially a blank value in memory has now been overwritten by window.default avatar. Now we know that we can reference these with the index numbers, but that's not important here because the source code doesn't make use of the index numbers when assigning variables. What does the source code make use of? It makes use of .avatar. We have a look at window.default avatar.avatar. We can see that we have this HTML element, which was the second anchor tag that we injected as part of that HTML comment. Now, taking a look at the comment section, we can see that our post specifically still has the default avatar. That's because at the time of our comment loading, the window.default avatar property had not yet been clobbered. So in order to unleash the power of clobbering here, we need to write a second comment so that when the avatar logic is performed on this new comment, it will be after the DOM has already been clobbered by this new window.default avatar property. So let's create a new comment. We're just going to call it test comment. The values are really not important here. We just need to make sure we pass the verification. That's all. Let's choose post comment. Let's head back to blog. So scrolling down, we see that the new comment actually has a symbol instead of the default avatar. Let's have a look at the DOM over that image element. So we can see the HTML for the image. Now we probably remember this being written in the JavaScript as part of a string. We have image class equals avatar, source equals. Now we actually assigned the value of source to an entire HTML element, an anchor tag. We can see the result of that. It appears to be a URL with a base path / and then the value of the href attribute that we included, Zen shell in this case. The question is, why do we have all of this base path here when we didn't include it as part of the href attribute? Also, when we say that we assign the value of source to a HTML element, that's only partly true. Because remember, we were actually writing this HTML in a string context. We were concatenating values to each other. And one of those values that we were concatenating was a HTML element. What happens when we try and concatenate a HTML element to a string? The HTML element gets converted to a string. In other words, the value of source here is actually the string representation of the anchor tag. And that just so happens to be the same as the href value. Let me prove it to you. Let's head back to the console. We know we have window.default avatar.avatar. What we can see on the screen right now is the anchor element that's being referenced by this HTML element object. What happens now if we call window.default avatar.avatar.toString? This is a built-in JavaScript method on this particular object. This is also what's happening to the HTML element when it's concatenated as part of that string. The .toString method is actually called behind the scenes. So when we call the toString method on this DOM node, here is the result. It's a fully qualified URL. To put this simply, when we call the toString method on an anchor tag DOM node, the output is actually just the value of the href itself. Now, this should start to give us some ideas because returning to the DOM itself, we now understand that we are actually injecting into the source attribute of this image tag. Now, in order for us to enable a cross-site scripting attack vector, the logical thing here is to try and break out of this source code and include some kind of on-error attribute. And of course, when that fails, we can call a JavaScript alert function. Let's load up a fresh post simply by changing the URL to post ID = 2. And let's try a fresh attack vector in this case. So inside the href attribute here. Now, unfortunately, we can't just close the href attribute and then type on-error equals and pass an alert. Why not? Because remember, there are two stages to this attack. First of all, this HTML is published to the document. Then the value of href is used to inject into the newly created image tag. In other words, if we close this href tag early, well, anything after that's not going to be considered as part of the injection into the image tag. So our payload has to fit inside these two inverted commas. On error is not going to be considered here. Now we know we can't simply use a double quote because that actually closes the href attribute. So what's the next logical step here? It's to see if we can make use of a HTML encoded double quote. So we do that in HTML with ampersand, QUOT, and a semicolon. The hope here is that this will be decoded as an actual double quote as part of the HTML inside the image tag, which is then going to close the attribute and allow us to make use of an on-error attribute. Spoiler alert, it's not going to work in this case, but this is the logical next step in probing for a vulnerability here. So we can call onError attribute equals alert. Okay, let's fill out the arbitrary values here. Let's choose post comment. Let's head back to blog. Let's also create a new test comment. Okay, so taking a look at the output here, let's take a look at window.defaultAvatar.avatar, see what we have. So we can see that we have the href attribute, and we've obviously been able to inject that double quote as part of the href attribute. So we can see it's inside the href attribute that's been posted to the page as part of our initial comment. The reason why it's not terminating the href attribute is because it was HTML encoded. So it's being interpreted as a pure double quote rather than something that's functional as part of the HTML on this page. So this is a good first step. Now, what we see on the screen right now doesn't matter too much. What actually matters is the toString value of this particular anchor tag. So let's have a look at window defaultAvatar.avatar.toString. Let's have a look at how this translates into a string, because this is ultimately the value that's going to end up as part of the source attribute on the image tag for the avatar. Now we should be able to see straight away that there is a problem, and that is that our double quote has been URL encoded as part of this toString method. So we get to the end of Zen shell, we then have %22, which is the URL encoded value of the double quote. In other words, it's not functioning as a double quote, which means that it won't break out of the source attribute on the image tag. And we can confirm this if we head back to the DOM. You can see the avatar that's been injected. We have image class equals avatar, source equals, and we see that URL string that we've just seen injected into the source tag. When we get to the %22, the hope here is that this is an actual double quote that's going to close the source tag and allow us to include an on-error attribute as part of this image element. So we've completely failed here, and the thing that's preventing us from breaking out of the source attribute is the fact that that double quote is being URL encoded and considered part of the source attribute string, which we don't want. So at this moment, we're stumped. We need some kind of workaround. Okay, let's head to post with the ID of 3. Let's start with a fresh post. Here is where we need to start breaking out the counterintuitive features of HTML. What we'll consider here is how the usage of the CID directive impacts on the way that a href attribute is translated into a string. So a CID attribute looks like this: href equals CID followed by a colon. It stands for content ID. And there's a chance that even if you're a web developer, you may not be 100% familiar with CID. And that's because it's not typically used on web pages. It's mostly used in HTML emails to reference something like an image without the need to reach for an external image file. So if an image is sent along with an email, it could be part of an attachment, for example, that specific image could have an ID and it can be referenced making use of CID. What we can see straight away is that typical usage of href attributes quite a bit different from CID usage of href attributes. And logically, it means the functionality of how such href attributes are turned into a string is also going to differ. So with our test file, hopefully remember this was under window.link.url. Let's just take a look at the element itself. Now let's call the toString method on this element. So it's going to turn the href value into a string. And right off the bat, we should see some significant differences. Remember how with our regular href attributes, we had that base path prepended to any text we injected? Well, that's completely gone now because this is not a regular href attribute. This is a CID href attribute. We actually just get the string that we've injected. So we've gained a little bit of flexibility here. Now, what we're really interested in is, does making use of CID have any implications surrounding the way that HTML encoded double quote will be dealt with? Well, let's find out. So in our second anchor tag, let's inject a HTML encoded double quote. Let's type onError equals alert1. And just for comparison, let's do the same thing with our first link. We're going to inject the exact same text, but we know that our first link is not a CID href attribute. Okay, so window.link. Let's make use of our index numbers just to keep things straightforward. So window.link at index 0. Let's simply reference the element first. Now let's call window.link at index 0 toString. So this is the non-CID. Okay, so we can see that we have the URL encoded double quote in the first toString conversion. Let's have a look at window.link at index 1. Let's take a look at the DOM node first of all. Now we can see just purely looking at the DOM node, it appears to be more or less the same, at least in terms of the href attribute. But let's have a look at the toString conversion. Window.link at index1.toString. Now that's clearly very different from index 0 toString. We can see index 0 toString, we have the URL encoded double quote. Index 1 toString, we actually have a pure double quote. There's no longer URL encoded. What that means is it's going to allow us to break out of the source attribute on the image tag for the avatar, which then means we can add an arbitrary additional attribute, which is going to be onError equals alert. Let's try it. Here's our payload. So this time we have href equals CID. We have HTML encoded double quote. We then have onError equals alert. Let's fill out the arbitrary information. Let's also post a test comment, again with arbitrary information. Let's post our comment. Let's head back to the blog. And now let's have a look at our values. So window.defaultAvatar.avatar. So here is our DOM node. Let's try calling toString on that DOM node. Now let's have a look at what we've actually injected into the page. We can see the exploit hasn't worked just yet, but we are extremely close. There's a little bit of tweaking that we need to do. So we have source equals CID. We've actually managed to inject an onError attribute, but there's a little bit of a problem. It's not a huge problem, but it's enough to prevent the exploit from working. We have onError equals alert1 double quote. That's actually just broken the JavaScript because alert1 is a valid JavaScript function. Alert1 double quote, that's actually broken JavaScript. In other words, we have a trailing double quote that we need to get rid of here. How do we do that in JavaScript? Well, it's JavaScript. We can just make use of a comment character. Okay, let's head to post ID number 5. Let's comment out that trailing double quote. Now, one of the subtleties here is you might wonder, well, why can't we just delete one of those trailing double quotes? Why can't we just pass this HTML? That way we've deleted one of the double quotes and the remaining double quote can simply close the onError attribute. Then we have working JavaScript. In some contexts, it might work that way. What we have to keep in mind here is that this is actually a two-stage attack. And if we submit this as our initial HTML, it's not actually valid HTML because now we haven't closed this href attribute. So we're not going to get a href value. This means that if we try and inject this HTML, then after we reload the page, window.defaultAvatar.avatar.toString is simply going to be undefined. It won't have a href attribute. In other words, we have to close a href attribute here for the initial HTML to be valid. But then obviously the end result of that is we get the additional double quote that we don't want. So what do we do here? We simply have to comment this out, and hence we end up with our final payload here. So now hopefully for the final time, let's fill out our arbitrary information. Let's head back to blog. Let's post a test comment. Let's fill out some more arbitrary information. Let's post our comment. Let's head back to blog. Notice straight away we get alert 1 popped up to the page. So we clearly have a successful cross-site scripting attack vector enabled by exploiting DOM clobbering. Let's follow the same script as before. Let's have a look at our values in the console. Window.defaultAvatar.avatar. So here is the DOM node. Let's call toString on that DOM node. We'll see the same as before, but we now have the JavaScript comment character. Now let's have a look at the injection point, which is the image tag. Here is the DOM for the image tag. We have source equals CID. We then have a very clean on-error attribute, alert1, comment characters, which comment out that double quote that we don't want. We then have another double quote, which is actually closing the on-error attribute. So the end result here is we have an image with an invalid source that's definitely going to produce an error. Then we of course have an on-error handler. What does it do? Well, it has alert1, it calls a JavaScript alert function, and it's valid JavaScript because that additional double quote has been commented out. Now we're almost there with this lab, but there's something else that Portswigger wanted you to pay attention to. Let's just read this in the guideline. Note that the site uses the DOMPurify filter in an attempt to reduce DOM-based vulnerabilities. So thinking about our exploit, think about the moment when we posted that initial HTML comment. Well, anytime a comment is loaded on the page, it actually gets passed through DOMPurify.sanitize. In other words, our HTML is not completely ignored and rendered directly to the page. Because the developer has made the decision to allow HTML strings to be posted as comments, there is some sanitization that happens on those HTML strings to ensure that they are not malicious. Now, one of the first takeaways here is obviously despite the fact that the HTML strings are being passed through .sanitize, doesn't necessarily prevent against all cross-site scripting attack vectors. So one of the mistakes that a developer could make is to assume, well, I have DOMPurify in place, so now I'm protected. Well, clearly not, according to the results of this lab. But it does beg the question, how exactly was it that we were able to generate a cross-site scripting attack vector despite the security mechanism being in place? So here's the DOMPurify library on GitHub. Notice the description here. DOMPurify is a DOM-only, super-fast, uber-tolerant XSS sanitizer for HTML, MathML, and SVG. And if you scroll down, we get to see some examples of the types of HTML that's going to end up being sanitized by DOMPurify. Seems that this is especially useful when dealing with HTML that's initially been put together as part of a string format. Of course, one of the things to think about here is, do you really want to be writing HTML as part of a string? Because anytime you're converting a string into HTML, there's a very high chance that you are introducing security vulnerabilities. So of course, one way of mitigating that is to have a library like DOMPurify, but the ultimate way of mitigating that is to not write HTML as strings and don't allow user input to become HTML, because there is an implication there that you are converting a string to HTML at some point. Now, taking a look at some of the examples here for the DOMPurify.sanitize method. So take the first example there. We have HTML string, image, source equals X, on error equals alert1. Probably thinking to ourselves, well, that's more or less the exact payload that we used. And according to the docs here, well, DOM sanitize is supposed to change that specific HTML string into the benign image source equals X. DOMPurify realizes, okay, this on error equals alert1 is malicious. Let's strip that from the HTML string, the HTML that ultimately ends up being part of the page, image source equals X. Interesting. So how exactly did we get that through then? Because surely that on error equals alert should be stripped, right? DOMPurify sees that there's an on-error attribute, sees that it has maybe alert1 or some other malicious-looking JavaScript, so it just removes that from the HTML. Well, here's the interesting thing. Take a look at our injected HTML one more time. Is there an on-error attribute that calls the JavaScript alert function? I can see why you might think there is, because it does say here, for example, on error equals alert. But looking at this anchor tag, it doesn't even have an on-error attribute. Remember, all of this on-error equals alert is actually smuggled inside the href attribute. So DOMPurify is looking for an on-error attribute. So it can say, actually, that's malicious HTML. We can't have that on-error attribute there. Is there an on-error attribute in this HTML string? No, there's not. There's a href attribute. Not too worried about that. As long as there's no on-error attribute, then this is a perfectly safe HTML string. Because remember, initially, if we have a look at the initial comment in the DOM here, inside this paragraph tag, take a look at the HTML that's been rendered to the page. There's no on-error attribute there. Simply href equals CID, on-error equals alert. So the reason why we've bypassed DOMPurify here is that we've smuggled this on-error attribute inside the href attribute. It's only at that second stage where the image tag is created that this onError attribute is removed from the initial href attribute and now placed as its own separate entity, the onError attribute. By that stage, the DOMPurify sanitation check has already happened. We've already rendered this HTML to the DOM. There's no further DOMPurify sanitization check that happens at this stage. Now, one thing you could say as well, hold on. I understand that onError is not its own attribute as part of this string, but surely this is something that DOMPurify should have picked up on. At the end of the day, this HTML string is clearly passed to DOMPurify, and even if onError is part of the href attribute, this is something that DOMPurify should have detected. I'm sure someone at DOMPurify could give you an answer. And part of the reason why we were able to bypass DOMPurify in this case is because on its own, this is not a malicious payload. It's only because there's a second step where this element is then used to generate a second element, and that's where the vulnerability is introduced. So you could also argue that actually this should have passed the DOMPurify sanitization check because on its own, it doesn't do anything. It doesn't have an onError attribute. When we first load up our initial comment to the page, there's no vulnerability there. It's only when we load up a second comment that then relies on this particular HTML element that the vulnerability is introduced. So this is not by itself actually dangerous HTML. There's a two-stage process to the attack here in this case. So it's not even clear whether it would be correct for DOMPurify to actually prevent this HTML string from hitting the page. Okay, so I would describe that as a fairly intensive lab to understand all of the moving parts. Some of the key ideas here are as follows. Understanding the non-standard browser behavior of assigning window properties based on element IDs. Understanding that multiple elements with the same ID form a HTML collection in some browsers. Understanding that elements in a HTML collection can be accessed by their name attribute. Understanding the concept of clobbering in general. Understanding HTML encoding and URL encoding on a reasonable level. Understanding the CID Content ID Directive for href attributes. And just a general understanding of using injection attacks to break out of element attributes. And finally, the behavior of toString when called on anchor tags or when concatenating anchor DOM nodes. All right, that's pretty much it. Thanks very much for checking out the content. Look forward to catching you guys in the next lab.